Okay, so we've done graphic and numerical techniques, and so 1.5 to 1.6 is going to be doing analytic. Now, for most students, including myself, analytic is going to be your favored strategy because it's the quickest, okay? So, two objectives, we're going to evaluate a limit using properties, so we'll go over those, and evaluate a limit using dividing and rationalizing techniques for those that don't work for the first way. So a value of a limit can easily be evaluated by using direct substitution. So this is going to be your first strategy that you always try. If you think of the idea of the graph, if my graph is continuous and my y values lead up to it from the left and the right, and it also has a value at the target value, then it will all be the same, okay? So the function does have to be continuous, which means it cannot be undefined. So in our first section, these techniques would not have applied. So the limit as x approaches, remember c is your target x value. Is equal to the function value. Okay, so it's saying the limit value is going to be the same as the function value when you substitute c. All right. So some basic limit laws is if you have the limit as x approaches c of a constant, which is just going to be a number, then your answer is always going to be that same number. So think about the graph. Like if you had y equals 3, let's say, well, you'd go up to 3, the graph, the y values are always going to be 3. So no matter what your target is, the y values from the left, the right, and at the target are always going to be the same number. So the limit as x approaches c of our function, so now we just have x, which remember is going to be a line. It's just going to be whatever number you're plugging in, okay? And if we have an exponential, so remember x is the variable, n is a number, so the n is going to stay. This is what you're substituting. So you have to remember the notation. X is the variable and c is the target x value. All right? So let's do some examples. So if we have the limit as x approaches 4 of x cubed, well, let's try substitution. Yep, 4 cubed is defined, so we would just get 64. My next example should look like number 1. This is just a constant number, so it's always going to be a y value of 23. And then this one, as the limit as x approaches x7, substitute, and we do get 7. Okay? So you don't have to memorize the 3 limit laws. Just memorize the strategy of direct substitution. If it works, then that's going to be your limit. All right? So some properties, and these look a lot more confusing than what they need to be, but they're going to define if we have the limit of f of x, the limit is L. And if we have the limit of g as we approach the same x target, that limit is k. So these are just going to be generic values. What that says is if we have a scalar multiple, well, you can kind of think of this scalar multiple being kind of factored out. And I'll write this once, but this is the idea mentally of why it works. It's kind of like an informal proof. Well, this, by substitution, is what we were given. That's L. So then we would just get whatever that B value is times our L limit. Okay? And that's the same idea here. I'm not going to rewrite all of these, but we're not distributing the limit, we're applying the limit to each of these separately. So the limit of f of x is L. We don't care if it's plus or minus, and then the limit of g is k. So you would just add those separately. Okay? Same thing with multiplication. We can apply the limits separately. So the limit and the limit of g. Division also works. You can apply them separately. So L divided by k. And it also works with exponents. So we're going to apply that limit, and that in whatever power that is can stay. All right. So let's look at our next examples. So these are going to be in general. They're going to tell us that the limit of f is p, the limit of g is j, and the limit of h is 5. These are just known. We don't care what the functions are, and they all have the same target. That will be the case. We're not going to try to trick you, okay? So you just have to remember, oh, if we're adding these functions separately, I can do their limit values separately. So the limit of f plus the limit of g, and since we've applied the limit, that limit notation no longer applies to our answer. It's just p plus j, whatever that is. Same thing here, we have a cubed. Well, I know I can just ignore the cubed for now and apply the limit of h, and then I cube it, and you can leave your answer like that on an AP exam, or you can write it out. You get full credit either way. And the last example, I've got, well, these are being multiplied, so apply the limit of f. When you multiply the numerator, apply the limit of g, and apply the limit of h. There's really nothing to reduce, so that's how you would leave your answer. Okay, so those are limit properties. All right, trig functions. Everything in trig you want, if you're using a graphing calculator, or your answers will always be in radians. Remember, that's from like 0 to 2 pi. I don't typically convert, so we'll want to get better working in radians. And we don't do trig a lot, so we're going to get just a little crash course refresher as we go, because it really depends on what we need. So we are going to try direct substitution, okay? So tangent, tangent does have some undefined values, but if you remember the graph, and then it just keeps repeating. This is way back from whatever, secondary 3, pre-calc, whatever class you were in. So at 0, well, we're actually defined, so if I try substitution, I can take the tangent at 0. You had to memorize, well, that is actually also 0. All right. This one, we're going to try direct substitution, plugging in pi, and see if it's undefined. So pi times the cosine of pi, and we're going to do a little refresher on our wave, because this is how I get most of my answers. This was pi over 2, this was 3 pi over 2, and one full cycle is at 2 pi. Cosine started at 1, and it went 1, 0, -1, 0, and then back up. And these are all going to be the popular values. So you should be doing these typically without a calculator, okay? So I've got pi, and then the cosine of pi right here is -1. Since that's not undefined, direct substitution works, and our limit value is -pi. Okay, quick review on sine. Same important values. For sine, it starts at 0. It goes up to 1, back 0, down to -1, and back at 0. Okay? So if we want to evaluate, we're going to plug in 0. So we're going to rewrite this as the sine of x squared. That's really what that notation means. So we're going to try direct substitution. And the sine of 0 is not undefined. There aren't any undefined values. So the sine of 0 is 0. So 0 squared gives us 0. 0 is a good limit value. Remember, it's a y value that we're trying to describe. We don't know what the graph of sine squared looks like, but we can use algebraic techniques, and direct substitution is always your first goal. Okay, so let's look at example number 2. I'm sorry, not example 2. Finding the limit of a rational function, kind of our topic number 2. Okay? So on this one, ooh, this looks pretty complicated, and so it kind of looks like our day 1, but remember, we want to try direct substitution and see if it's undefined. Well, we're not going to get undefined in the denominator, so far, algebraic techniques are going to be our go-to. 1 plus 1 plus 2 is 4. 4 divided by 2, so 2 is our limit. Okay, let's try this one. Limit as x approaches 1, we try 1 cubed. Now this problem, if you recognize it, this was from yesterday. So what that means is that substitution does not work, okay? Now, that doesn't mean that it doesn't have a limit answer. We actually know the answer, but we need to figure out how to do that algebraically, because I don't expect you to know what this graph looks like, and making a table will take you way too long. So we tried direct substitution. After direct substitution, you typically want to try to factor. Now, this is a long factoring technique. I called it SOAP when I taught it, but this would be something that you would have learned in secondary 3 class. So you want to write this as x something cubed minus 1 cubed. And then it's going to be a binomial and then a trinomial. So it's always going to be the first number, the last number, the first number squared, multiply these together, and then square the second term, okay? And then the signs are SOAP. So SOAP stands for the same sign as what you started with, the opposite sign, and then always positive. Okay? I know that's drive-by factoring review of a cubed. The denominator is going to stay the same. And we still have the limit. Since we have not evaluated the limit, you technically need that notation. All right, now we're going to try to these reduce. And so I'm just left with this numerator, and now once you've factored it and reduced, now you want to try to go back and do substitution. Well, it won't be undefined anymore because we don't have a denominator. So if I try direct substitution, we get a value, and we know from yesterday that that is our limit value. Okay? All right, let's look at our last example. This one, if I direct substitute 0, I get undefined. So direct substitution doesn't work. That is not something that gets factored. So our strategy is going to call it rationalization. So these are your algebraic strategies, okay? I'm going to summarize it. So number 1, you always try direct substitution. 2, try factor. Then go back to number 1. Number 3, we're going to do rationalizing. And then go back to number 1. So this one, we don't rationalize the denominator. We want to rationalize the numerator. So we multiply that by the conjugate. And I know this has probably been since secondary 2, so it's been a while. So the conjugate, we're going to multiply. You keep the first part the same, and you do the opposite of the second part, okay? And we're going to do that on top and bottom, because that's like multiplying by 1. So the limit is still there. We're just going to manipulate this algebraically. So we're going to have to distribute. So root times roots cancel, and you just get what's inside. Then I'm going to have plus that root. Then we're going to do the inside. So that's minus the root. And then -1 times +1. On bottom, we're going to leave this in that factored form. And this is usually always, okay? You'll see why in a second. And it's still the limit as x approaches 0. Okay. So these terms cancel. These terms cancel. So I'm left with x over x and still the limit. Well, the x's cancel, so I'm left with a 1 on top. And now I want to try direct substitution and see if we have a defined value. So I would get 1 over, that's gone. So we have 0 plus 1 plus 1. So 1 over, well, the square root of 1 is 1, 1 plus 1 is 2. All right, so we've got numerically with tables, graphically if they give it to you, but then algebraic strategies are going to be the ones that you need to practice. Okay, so good luck.